Okay, let's make a start then. So what I'd like to do today is to go through this stuff about ensembles and classifiers. And we did a little bit of this last week, but it was cut short because of the technological problems. So I'll go through the beginning bit quite quickly, because we had a look at that on last week, but I'll just go through it quickly to set the context for the rest of the talk. So we talked last week about this idea of an ensemble of classifiers. So we had this idea that we've got some kind of classification algorithm. So you want to classify stuff, and the usual way to do that, you've got a training process which takes some data set, puts it into a classifier, and that produces something that we might call a model or a predictor. It produces something which, when we put a new data item into it, so we put a new piece of data, some unseen data, and it gives us some kind of prediction as to the class of the outcome. So this training process here, so we've got a kind of training process there, and then we've got a kind of test, or test, an actual real use of the algorithm. This is what you'd actually use for real. So what happens? Well, we've got a data set, and we've got some kind of algorithm that creates classifiers, creates models, and this classification algorithm uses some kind of idea of attempting to build a classifier, and that classifier is driven by error measurements. So we've got some kind of idea of measuring the error or the accuracy of this. And these ensemble methods, rather than having a single classifier, have multiple classifiers. So you've got you've got different classifiers, C1, C2, different the classification algorithms being run multiple times. That's what this is, and they produce different classifiers or different models or different predictors, whatever you want to call them. So at the end of this process, so you do this learning process multiple times. Each one of these produces a model. So each one of them produces something like a decision tree or a trained neural network or something like that. And the idea of these ensemble methods is then, when we've got a new piece of data, we feed it into each of these models, and then we get something out from it, which is a prediction. So we get a different prediction for the same piece of data. We get a different prediction, and then we do some kind of voting. So we say P1 was, let's say there are two classes which are true and false. So P1 might say, for that piece of data, the thing we're interested in is true. For that one it's true, and for that one it's false. So we do 2 votes for true and 1 vote for false, and so we conclude true out of that. So that's the basic idea of these ensembles of classifiers. So there's a number of things we might think about here. One is this to do with this accuracy of these classifiers. So we might say, does it matter whether they're each individually very accurate, as long as altogether they give us an accurate answer? And one of the arguments here is that it doesn't matter. The individual accuracy isn't very important, that we can use these sorts of methods to take what are often called weak classifiers, that is, classifiers that don't make a very accurate prediction, and bring them together to form a strong classifier by putting lots of weak classifiers together. But the important thing is this diversity. So if you do this process and all these classifiers produce models that make the same prediction, then that's pointless. You're just going to get the same result out, and so there's no need to do that. So you want some idea of diversity, some idea of different classifiers producing different results. And of course there are computational cost implications here, yeah? If we're running a classifier 20, 200, 2,000 times rather than once, then obviously the time it takes to build that classifier, composite classifier, that ensemble classifier, is going to be a lot larger. So that's that thing. This is the introduction. And this is basically what I said, yeah? So if classification is performed by a single classifier, it has to have a high accuracy, but it's not crucial that each classifier has a high predictive accuracy if we're voting between lots of them. We need some idea of each classifier being reasonably accurate. Obviously, if they're all telling you nothing, then the ensemble tells you nothing. But if they're reasonably accurate, importantly they're diverse, they each are accurate on a different part of the data space, for example, and the other errors that they make are random, uncorrelated, then we can put them together with voting. And so last time we had a look at this example, didn't we? We said that if we got classifiers which had an accuracy of 60%, so they have an error of 40%, 0.4, then the worst they can do is all give you the same error, yeah? So the worst thing you can do is each one of these models basically gives the same profile of errors, and so you get these votes are always either all true or all false, or whatever the thing you're trying to classify is, and so you don't benefit. But you don't get any worse by that. You know, that doesn't make it any worse. That just means that you get the same errors using one individually. So that's just a computational efficiency problem. But if we put them together, and the different classifiers, the different models that have been produced are uncorrelated with each other, then we might be able to improve the accuracy. And so we looked at this example last time. We said the best thing to do is for the classifiers that are generated, the classifiers that have been learned from this, if they produce very diverse results and the errors they produce are uncorrelated, they're independent, then this voting procedure will bring things together in a positive way. It will make a prediction that's more accurate than the classifiers used separately. So we looked at this example, didn't we? And we said that basically, if you've got this is quite complicated, so it's worth going through this in a bit of detail. So we have the idea that we've got basically lots of different ways in which you can make an error. So you can have the situation where all three classifiers make an error, or two of them make an error, or one of them makes an error, and none of them make an error. And essentially there's one way of doing each of these, yeah? You can either get them, you know, all right, so you get them all wrong or all right, but then for the ones in between, there are three ways of doing this, yeah? So there are three ways of making two errors and three ways of making one error. So if we look here, this is done it by enumeration, yeah? We've looked at the three possible ways in which you can make two errors here. So you can either get it right on classifier 3, you could get it right on classifier 2, or you could get it right on classifier 1. So there's no other way in which you can make 2 out of 3 errors, yeah? That's the only three possibilities. And so we say that we think about this voting process, yeah, and think about these different ways of making errors. So if we make no errors, we're fine. Voting, are all 3 votes are correct, so that's alright. We make 1 error, then this is where we're starting to get some advantage, yeah? We've got 3 classifiers, 3 models for this data. 2 of them make the right prediction, 1 makes the wrong prediction. So the voting in total is for the right one, so you end up alright there. The 2 cases where the ensemble, the collection of these classifiers, makes an error is in when 2 of them make the error and outvote the one that is correct, or the one where all 3 of them get it wrong. And so what this example was about was calculating the probability of getting things in these 2 classes. So the table there is about this bit, yeah, where the 3 classifiers, where of the 3 classifiers, 2 of them make an error, and we can calculate the probability of that, yeah. We can say that the probability of that is the probability of one making an error, probability of the second one making an error, times the probability of the other one getting it right. And there are 3 different ways to do that. So we can add those up, or more importantly, we can just multiply that by 3, because multiplication of decimals is commutative, no matter what order you do it in. So you're always going to get that same probability out at the end, yeah. So so you can say that there are 3 ways of doing this. They've all got the same probability. So you multiply that probability by 3. So that's the probability of 2 of them making an error. And then we can calculate this other case here, this case where 3 errors were done, and that's only one way of doing that, which is for each of them in turn to get it wrong. And so we can calculate the probability of that. And then we add those together and we get approximately 0.35 out of that. And that's better than the single classifier's error of 0.4. So if we carry on with this, and this is where we got to at the end of last time, when we were going through this a bit quickly in the short time I had last time, we looked at how we can generalise this argument. And so one difficulty with generalising this argument is that whilst for 3, if we look back at the previous slide, for 3 errors we could make these tables and we could enumerate the different ways of making these errors. You don't want to carry on doing that forever. What you want to do is just count them. So we said that there are these measures, which I think you've probably seen, these ways of counting things. So we say that C of the number of combinations of R things out of N is given by some formula, which is the factorial of N divided by the factorial of, which way around have they put it in here, of R minus the factorial of N minus R. And I won't go into reasons why that's true, but you can look that up if you want to know. And so that gives us a way of counting things, yeah? That gives us, what that means is the number of ways out of N things that we can choose are combinations of them. So here, if we've got 3 things and we were trying to choose 2 of them as being errors, then we look at choosing 2 things out of 3. And if we do the math on that, we get 3. And so we can do something similar for this ensemble, this larger ensemble now. We can do 5 classifiers together. So the ensemble makes a wrong prediction if 3, 4 or 5 classifiers make the wrong prediction, yeah? So why is that? Well, that's to do with the voting process, yeah? If you're making a prediction and you've got 5 votes, then if everyone's wrong, or if 4 people are wrong, or if 3 people are wrong, if all the classifiers are wrong, if 4 of the classifiers are wrong, if 3 of the classifiers are wrong, then you make the wrong prediction, otherwise you get it right. And so you can do basically the same calculation we did on the previous slide. We say, what's the probability of 3 of them making an error? Well, there's this count, this number of combinations, the number of different ways of choosing 3 things out of 5. There's that many ways of making those errors. That's basically saying how many lines are there in a table like this. So there's that number of ways of doing it. And what's the probability of doing that? What's the chance of doing that? Well, it's 0.4 times itself 3 times if there are 3 errors, and 0.6 times itself 2 times because there are 2 ways of getting it right. And so we do that for 3 errors, for 4 errors, and 5 errors. And if all these are mutually exclusive, we can just add these up. So we can do the math, and then you can add those up to get a total probability of this combination, this ensemble of these 5 things making an error. And when we add those together, we eventually find that our error rate goes down to about 0.29. So we started with one classifier with an error rate of 0.4. We then looked at 3, and we said that it was about 0.35. And we looked at 5, and we said it was 0.29. So we're improving as we put these things together. So that seems to be a good thing. So we can do this, and eventually this stops improving. This works for now, but we can't just keep on doing this forever. Partially because we can't always generate the classifiers that are diverse enough. We're making this big assumption here that we can generate lots of classifiers that make entirely independent errors from each other, and that's not always going to be possible. But for the first few, it usually helps. And actually choosing the number of classifiers so that it's still productive is quite difficult. There are ways to do it. You can just keep adding them until it starts to flatten off, or there are more sophisticated ways of doing it. But it's difficult to know quite what's the best size for these ensembles. So I'll come back to this in a minute. I just want to motivate this to a different direction, and then this will motivate using these ensembles in a different way. So this is quite a complicated idea, this idea of bias variance trade-offs. And I'll give a simple example of this. So where this comes from originally, this idea, just ignore what's on the slide for now, but this idea of bias variance decomposition comes originally from an idea to do with insurance and the statistics of insurance. I think this is where it comes from. This is certainly the example I've seen to motivate it. So let's say we've got some disease that you've got a 1% chance in a year of getting that disease, and then you want to, if you get that disease, you need a certain amount of money to cure it, which is £10,000, let's say. So you've got a cure that, if you get it, costs £10,000. So the cost, the expected cost to you in a year of that risk is £100, yeah? So you've got £100, which is what you would expect to have to pay typically. This is a 1% chance of you getting it, and if you get it, it's costing you £10,000. So, okay, fair enough. But we don't want to do that. We might not, we're fairly unlikely to have £10,000 lying around just to pay for this treatment as we need it. So we outsource that risk, we outsource that variance, that chance, by taking out insurance. So you go along to the insurance company, you say, I've got this, I've got this, I want to insure myself against this disease that I don't know if I'm going to get in the next year, but you know that there's a 1% chance that I'll get it. And they say, right, okay, so that's going to be, we're going to charge you an insurance premium of £150. These meant to be pound signs, they look more like euros. So I'll charge you £150 for the year to insure you against that disease. So there's something happening here which is interesting. The cost to the insurance company, on average, is £100. For per person that takes out that insurance is £100. But they actually charge you £150. So they're making some profit. They're making £50 profit, which is a perfectly reasonable thing to do. They're actually, they're taking risks. They're actually taking on the risk for you, and they think that that's worth it to them, to this amount. That's what they, that's what they judge that they can charge people, that people will be prepared to pay. And we call this bias. There's a difference between the actual cost to the insurance company and what they're going to charge you. So they take on that risk and they charge you for it. They make a charge, which we call the bias. And what they've done is they've reduced the variance. So previously, you had a 1% chance, before you took out insurance, you'd have 1% chance of paying £10,000 and a 99% chance of paying nothing. So on average, whatever average means here, you'd be paying £100. But of course you're never paying £100. You're either paying 10,000 or nothing. But now, after you've taken out the insurance, you've got a 100% chance of paying £150. So what you've done is you've decreased the variability. So you've decreased the variance in what you will pay. You've decreased it from quite a large amount. There's a large variance there, and you've decreased it to nothing. You now know exactly what you're going to pay. But the trade-off there is this bias. Under this, your expected outgoings are £100, but now your expected outgoings are £150. So you've in the pre-insurance thing, you've weighted variance more than bias. You've said, I'm prepared to accept that variance, but for basically an unbiased cost. Whereas when you've taken out the insurance, you've tipped the seesaw a little bit the other way, and you've said, well, I'll take that variance, I'll take that reduction in variance, but I'll pay a cost for it. And this comes into machine learning as well. So, having given you that as a motivating example, let's come back to this example about machine learning, about data mining. So, let's think about decision trees. Yeah, you've got a decision tree. You look at some piece of data. You make a choice based on that attribute, which way round the decision tree to go, and eventually you come up with a leaf node which tells you which class that example should be put in. Yeah. So, classic examples like weather prediction. Yeah. Is it going to rain tomorrow? And you can look at various characteristics, and you can say, well, did it rain today? If yes, predict that it will rain tomorrow. If not, has it been cloudy today? If yes, predict, yes, it will rain tomorrow. If not, was the temperature below 15 degrees today? If not, then predict. No, if yes, predict yes or something. So you've got some kind of decision tree, and this is very fine-grained, yeah? You've made a decision by looking at various pieces of data. The other thing to do would be to cut that off there and to say, did it rain today? If so, predict that it will rain tomorrow, otherwise predict that it won't. Now there's a kind of trade-off here. We've got a similar trade-off. With this one, we've split the space of data down into large numbers of examples, yeah? So we've said we initially make this choice, and then we break that one down, and then we break that one down. And so this decision boundary, as it's called, this way of breaking down the space of attributes, is very fine-grained for that one. And for this one, it's not very fine-grained at all. We just split it into two regions, yeah? So what's happening there is that this is much more accurate on the training data, but this is much less accurate. But this is prone to what's called overfitting. Have you heard about overfitting before? This is very much fitted to that specific set of data, yeah? It's not very flexible. So perhaps this decision here to split this group up was a bit arbitrary. Actually, if you add a few more data points in, perhaps there's a bigger chance in the overall, you know, the data set you're sampling from, perhaps there's as big a chance of there being a negative in there as there is a positive in there. So making that distinction just on 3 items of data, that might have been over reliant on the data you've got. So there's an analogy with this here, essentially. Here you're paying a cost. You're paying a cost here, which is that you're not making such accurate predictions. But the side effect of that, the kind of compromise, is that this doesn't have the same variability. If you've got slightly different data, if the data set you sampled was a bit different from the data set you've got there, then this is relatively insensitive to it, yeah? You know, you get that same inaccuracy almost regardless of what the data was like. Whereas this is very accurate, but if you change the data a bit, if you change that plus into a minus and that minus into a plus, then suddenly you're getting a lot of inaccuracy. So we've got that same sort of trade-off as we had with this example. So you say, you know, the pruned tree has got a larger bias, in the same way that the person who took out insurance has got a larger bias. They're paying a cost for that. So, you know, this is basically what I said. You know, if you use the same classification algorithm, depending on precisely what data set you've got, those prediction errors have got some kind of variance that's determined by that variability of the training data. So we've got a kind of trade-off here. We've got a kind of seesaw. We can, you know, at present we can choose one or the other. We can either choose to prune the tree or not to prune the tree. But then you start to think, well, does the ideas that we talked about earlier, these ideas about ensemble methods, about collections of classifiers, do they allow us to have the best of both worlds? You know, can we, rather than this being a seesaw, can we actually have it so we've got both as being high? And up to a point, yes, is the answer. And that's what some of the techniques that I want to talk about now are about. They're about this idea of, rather than choosing between these two methods, so here we said we can either do this or we can do this. But what if we did that and that? What if we deferred the decision to the end? What if we took both that decision tree and that decision tree and 100 other decision trees with different amounts of pruning, different amounts of this trade-off, and said instead of saying this is the definitive decision tree, what we're going to do is we're going to make lots of them, and then we're going to let them vote. And so perhaps if the data is very variable, perhaps these start to dominate and they win out in the voting. If it turns out there's not so much variability, then these much more accurate trees are going to win out the vote, and we're still going to be alright. So that's the idea of some of these techniques called things like bagging, bootstrap aggregation. So there's this idea of bootstrapping, which is it's a strange term. There's this idea of it's a statistical term which means taking items from the original training set to get a new data set. So often we want lots of data, yeah? Typically, as long as we're sampling in an unbiased way from what's out there in the world, the more data we can get, the better, yeah? The more accurate our predictions become if we've got more data. So, one problem is we've often only got a certain amount of data, yeah? We've got a certain number of items of data, and that's it. We can't collect any more. It's expensive, or it's hard to collect this data. So you've got a certain number of data items in your data set. And so you say, well, is there some way of artificially creating more data? Well, bizarrely there is, and this it's slightly weird why this works. So there are good theoretical reasons for it, and that's that you create some subsets. So you've got your original data set, and you pick a few things at random, and then out of those data you create a new data set. And then you pick a few more at random, like that. And sometimes you'll pick the same one again, and then you put those together to form another data set. And you pick some more at random, and then you've got another data set, yeah? And so each one of these you can then treat as an independent data set and build some kind of classifier on them. And this seems to give more accurate results. Somehow you're feeding these independent subsets of the data to different classifiers. These individual classifiers aren't going to be very good, but when you put them all together, they can be more powerful than creating a single classifier from all the data. So you create each of these samples, which is called a bootstrap sample. This thing about bootstrap comes from this expression about pulling yourself up by your own bootstraps, yeah? Which is of course impossible. You can't lift yourself into the air by pulling on your boots. But the idea here is you create a better prediction not by going out there and getting more data, but by sampling from what you've already got, which is where this name comes from. And so then you've got these different data sets. You train the classifier on each of these bootstrap samples separately, and you see if it's any better. And empirically, people have shown that the results of voting between these different bootstrap samples end up being better than doing a single classifier on the whole data set in a lot of cases. So what's going on? Why does this work? Well, this is a slightly waffly version of an argument that can be made very, very rigorous mathematically, which is that it reduces classification error because it reduces the variance associated with each of these classifiers. So the classifier we get from each of these is called a base classifier, and then we put them all together to form something called an ensemble classifier. So because these are drawn from a smaller set of data, they're going to have less variance. They're not going to be as variable in their prediction. And so when we put them together, that seems to reduce the overall variability. It reduces the overall error. And it's particularly useful when this original classification algorithm's unstable. So what does unstable mean? Well, an unstable classifier is one where it's very sensitive to the specific items that it's trained on. So if we think about a decision tree, that's an example of a classifier which is largely quite unstable. And the reason it's unstable is because of how it gets constructed, yeah? Think about that example that I'm sure you've seen, but back to this example about the weather, I'm sure you've seen in detail. You've got various characteristics. Was it sunny? Was it, did it rain today? What was the temperature high? You've got various characteristics, various attributes, and then from those attributes and those features, you say we're going to construct a decision tree. So we're going to make various decisions based on those features. And so what you do is you choose the best one, yeah? You choose the most predictive one first. You do this greedy method, yeah? So you say, let's say, was it sunny today? That's the first thing I'm going to look at. And then because my data, on the particular data set I've got, that's the feature, the attribute that's going to give us most predictive power. So I say, was it sunny, yes or no, and then I make another decision here about that, and so on, and that goes, goes down the tree, and eventually we reach some kind of leaf which says, yes, it's going to rain tomorrow, or no, it's not going to rain tomorrow, and so on. So we get these kinds of decision trees like this. Now, we could very easily have made a completely different tree. If there'd been a bit of variance in the data, been a bit of a change in the data, perhaps I start with rain instead. And then the whole sequence of decisions going down this tree becomes very different. So everything going further down in the tree becomes very different. So things like these decision tree algorithms have this tendency to be quite unstable because the early decisions can change everything else in the classifier so much. So these techniques like this bagging, bootstrap aggregation, they change, they allow us to compensate for the stability. They allow us to get around that a little bit. And then there are other techniques that are similar. So we've got a slightly more sophisticated technique, a slightly more refined technique which is called boosting, which has a similar idea. But what we do here is we've got a large number of training examples, yeah, so a data set consists of a lot of data, and then we've got all these data items, and initially we do a classification and it's going to get some right and some wrong, yeah? So we build a classifier, it gets those two data items right. Each data item's got some attributes, some features, and it's got a prediction that we consider to be the right one. So this might be the various weather measurements and whether it rains the next day. And that one, we run the classifier, we train the classifier, and it was right on that one, it was right on that one, it was wrong on that one, it was right on that one, it was wrong on that one, and so on. Now, with the original ensemble methods, we just train again on the same data set. But perhaps we don't care so much about these anymore. Yeah? It's got it right so far. So perhaps we want to focus the attention of the classification algorithm on these ones where it got it wrong. So the idea of boosting is that we boost the attention the classifier gives to that on successive rounds of training. So one way to do this is to associate a kind of score with each of these, yeah? So let's say initially we know nothing. So let's give a score of 10 to each of these items. Then they've all got a value called 10 associated with them. Now, the next time round, we want to focus on those instances where it got it wrong. So let's say it got it right, so we don't change the score, but it got it wrong, so let's put the score up to 11. So we add 1 to the score for each of those where it got it wrong. And now we need to somehow use this information to change how we train the classifier. So one way to do this is to use this to bias this choice of bootstrap samples. So perhaps rather than training on the whole data set, we make samples like we saw a couple of slides ago, and we say there's lots of these, so there's a chance of 10 out of however many there are times 10 of choosing that one. There's a chance of 10 out of how many there are total from that one. But this one's slightly more likely to be chosen. It's got a slightly higher weight associated with it. So we bias the choice of that one towards that. Then we do the classification again, and this time these were both correctly classified. That one was still classified wrongly, that one was classified wrongly, those were now classified right, and so on. So now we change the weights again, and we say, well, they're still alright, so they stay at 10. That one's still wrong, so its score goes up to 12. That one was wrong, so its score goes up to 11. They're now right, so perhaps their score goes down even, goes down to 10 or stays at 11 or something. So we have some algorithm that allows us to allocate scores to these based on whether it was the prediction was right or not, and then eventually we might get to the point where we're really focusing on one of these. Perhaps this is a really hard one to classify, so we really want the classifier to look at that lots and lots of times until we get some classifier that does it. And then again, we can use these ensemble methods. So each time round we get a classifier, and then at the end we put these all together and we make a vote between them.
Sorry.
Yeah.
Isn't it risky for that, because one value could be an outliner?
That's a good point. Yeah. So you could have some outlier. You could have something that was completely wrong. Yeah. It's
and
completely
a huge weight value.
So it could get a huge weight value, and you could get a classifier that was just trying to classify that one. But you'd hope that would weigh out in the voting. You're not taking the final classifier. You're taking all of them, and then you're taking a vote between them. So hopefully that weight, whilst some of the later classifiers in the ensemble were biased towards that one, some of the earlier ones weren't. So when you take the vote, you hope that would balance out. And so there are some ways of doing this by sampling but there are also some ways of doing this by modifying the classification algorithm itself. So I think this is basically a summary of what I've said on the board. Yeah, you've got a number of training examples. Each has got a 0.2 probability of being sampled. You do a round of boosting, and you sample 5 examples, which are 2, 4, 4, 3, 2. Build a classifier from that particular bootstrap, and then that classifier classifies 2, 3, and 5 correctly, and 1 and 4 are wrong. So the weight of examples 1 and 4 is increased, and the weight of the other samples is decreased. So now the second round of boosting samples 5 examples, but this time the ones that were classified wrongly are more likely to be sampled. So that's an example of that. So I just want to finish for 5 minutes by thinking about another technique, which is this random forest technique. And this is very effective. It's relatively new. It's been around for 10 years or so, but this is a really interesting technique that seems to work very well. And this is specifically about decision tree classifiers. So what typically happens when you build one of these decision trees is that each time you come to a new node, you look at all the attributes. You build the node, you build each tree in basically the same way, yeah? You go to a node and you say, what's the most predictive feature I could use here? What's the most predictive attribute I could use here? And you use some characteristic like information gain or information gain ratio to decide which one to put in there. So you put in rain or something like that, and then you look at this one and you say sunny, and then perhaps that way it was temperature or something like that. And you go on down the tree until eventually you make a prediction. Is it likely to rain today? You make some kind of prediction at the end. Now, the thing that happens here is you make each of these decisions in the same way. So if you repeat this algorithm multiple times, you're going to get the same decision tree out, yeah? So we said that one thing that was important for these ensembles was to get diverse classifiers. So how do we do that? Well, we introduce some randomness into how each of these trees is produced. So one way to do that is to randomly select a set of attributes. So at the beginning here, let's say we had 20 attributes. We had 20 fields, 20 things about today's weather that we're going to use to try and predict whether it's going to rain tomorrow. Well, in traditional decision tree methods, we would look at all 20 of those characteristics and say, which is the best one? Which is the one that's most likely to make the best prediction? But in this one, we don't look at all of them. In this technique, we don't look at all 20 of them. We pick at random, let's say 5 each time. So we select F, in this case 5 attributes, and we just choose one of those. So at the beginning here, we might not have access to the variable rain this time round. So we start by using the variable like sunny or temperature or something. So we construct one tree that starts with temperature and so on. So in that case we get a different tree. And we do this lots of times. So we get this collection of trees, this forest, and then we use that voting procedure to choose the best one. Another way of doing this is each time you need to make one of these decisions, you evaluate all of them. So you calculate something like information gain ratio, and then you say, well, I'm going to choose randomly from one of the 5 best rather than choosing the best. And so this is a way of getting a large number of these trees, and as I say, using traditional decision tree methods, getting large numbers of trees will be pointless because each tree would be calculated in exactly the same way on the same data, but so there'd be no point in repeating it. But this time you've used some randomness to construct each of the trees slightly differently, and so they're going to make slightly different predictions to each other. So again, we can use voting to make the best decision, and it seems that this works better than just using a single decision tree and using the absolute best information gain ratio each time. So overall, these ensemble methods seem to work well. You know, this random forests method is probably one of the best methods at the moment for doing predictive classification type tasks. So, just to finish for a minute, on the whole, these ensemble methods seem to improve predictive accuracy. There have been a lot of studies of these, and these different methods do very well. One problem is that we lose comprehensibility here. So, if I've got a decision tree with 5 nodes in it, then I, as a human being, can understand that. You know, if it says, was it sunny yesterday? Was the temperature high? Did it rain yesterday? I can understand that. And sometimes, for certain applications, we want to get a human comprehensible decision tree out of these methods. So some of these medical ones are a good example. Sometimes we're not using that in isolation, we're using it combined to give some guidance to someone who will combine it with other knowledge. But sometimes we don't care. Sometimes we just want the best accuracy possible. So, you know, it's impossible to understand. If you've got 100 separate trees, it's impossible for you to understand why it's making the prediction it is. But if all you care about is accuracy, which is often the case, then that's reasonable. And importantly, the diversity of these classifiers is important. So in this random forest method, we forced it to produce different decision trees, so that each one in the collection in the ensemble was different. So that's that, and we'll go on to a different topic tomorrow. We'll take a slightly higher view and look at the whole process about knowledge discovery and how these algorithms fit into that. Okay, thanks.